Okay, we're going to combine two lessons. You studied this last year, so it's kind of a review, but we're going to start first with composite functions. Composite functions, and the idea goes like this: you're going to be given two functions. F of x equals 2x plus 5. You're going to be given another function, g of x equals, for example, radical x plus 6. And the idea is you're going to, so let's just quickly from the last class, we know that the domain is all the reals, the range is all the reals for this one, and for g of x, what is the domain? It's x is greater than or equal to 6, and the range is greater than or equal to 0. And so the idea is you're going to be asked to evaluate the composite function. So they say evaluate, and they give you this funny looking thing. Either it looks like this, f of g of 2. You might see it like with a circle here, f of g of 2. But the idea is you have to evaluate this. And how are you taught to evaluate this? You're taught start from the center and work your way out. Start from the center and work your way out. Work your way out. And so the first thing you did was you evaluated g of 2, and you plugged it in there. Oh, g of 2? G of 3. Let me change to 3. G of 3. And so we got the square root of 6 plus 3, and that was radical 9, which was 3. And then you took the 3 and stuck it in the x. And so it was 2 times 3 plus 5, and you got 11. And so you say, okay, f of g of 2 equals 11. Let's just do a visual from my mapping. And so the idea is you started off with an x value, and then some function transformed it. You started off with a 3, and then the g function added 6 to it, and then took the square root. So that took you right back to 3. And then what did the f function do? The f function took the 3, multiplied it by 2, and added 5. So it took you to 11. That's what's going on here. So it's basically a composite function is a succession of functions. It's a function inside a function inside a function. So we're putting the radical inside of the linear. I might ask you to evaluate. You were asked last year to evaluate a couple of functions. So, f of g of negative 2. Right? So you go, okay, fine. First do g of negative 2. Negative 2 plus 6 is 4. The square root of 4 is 2. And then you take the 2 and evaluate that in the f function, which gives you 9. And so we say this was 9. Maybe you were given g of f of 10. And so you say, okay, fine, Mr. Adler, f of 10 is the f functions doubles my x and adds 5, so I get 25. And then g of 25, it adds 6 and takes the square root. Radical 31. Not the nicest answer, but you know what? No big deal, you can do that. Maybe I might give you some fraction madness. But then the question is, I don't want to keep doing this over and over, another case, you might have seen, f of like negative 2/3. Let's make it look like that. So, well, it's the same letter. Yeah, you're going to repeat it over and over and over again. So start off, first f of negative 2/3. That's equal to what? Negative 4 over 3 plus 15 over 3 equals 11 over 3. And then you're going to plug the 11 over 3 and stick that in the formula over 2. So double this plus 15 over 3. Final answer, 37 over 3. Not the prettiest answer, but whatever. the question is, let's say I ask you to do this several times. So the idea is, can I come up with a function that just represents f of x or f of g of x? And you learned last year you could do that. You know, once again, sorry, I erased that. 2x plus 5, and g of x is the square root of x plus 6. And so the question is, what is f of g of x? Well, let's think about it using mapping. What's the first thing we're doing? We're taking x. What does g do to my x value? It's turning it into the square root of x plus 6. And then what is f doing to this thing? Well, it's taking this thing, whatever's in there, doubling it, and adding 5. Final answer, well, we know this is x plus 6. Final answer, 2 radical x plus 6 plus 5. That's it. That's all it is. So once again, you're just putting a function inside of a function. That's it. What if I ask you to evaluate g of f of x? Well, you might say, okay, what's going on with the f function? It's taking x, and it's doubling it, and adding 5. Well, what is the g function to? The g function takes this thing, whatever's in here, it takes it, adds 6, and then takes the square root. Final answer, 2x plus 11. So you've created this, composite function. Nice. Now, the exercises in the book are just, very straightforward, and you're just figuring this out. For the higher level kids, there's a fun exercise. This is kind of cool. This is kind of interesting. And they say, if, this is HL, if f of x plus 1 equals 4x squared plus x, they want to know what is f of x. So I want you to shut the computer. It's in your book. Don't look it up. I want you to have fun. Figure that out. What was f of x? Once again, yeah. So you know what? I'm going to leave it up to you to figure it out. Next. The next thing we want to talk about is inverse function. Let's move on. Inverse functions. Now, we saw inverse functions when we were exploring exponents and logarithms. And the idea was, when we had y equals 2 to the x, we saw that this function took like 1, 2, 3, and mapped it to 2, 4, 8. And we came up with a function that we needed a function that took 2, 4, 8 back to 1, 2, 3. And we came up with logarithms. That was the idea of logarithms. And we kept it very basic. Logarithms I said we really didn't study anymore because the calculator, right? Logarithms do have a lot of purpose. Anyway, so the visual is, what's the visual here? We take an x, right? And f is bringing that x to y. But the question is, what does the inverse do? It takes it back to x. So f is the point xy, and the inverse, therefore, is the point yx. There's a lot of interesting combinations here. So the question is, I'm going to be from last year. Most of you studied last year. You were given a function, and you were asked to find the inverse. Right? So what happens here? Sorry, guys. So how to find the inverse function. This is the notation for the inverse function. It's not an exponent. When you see f negative 1, you say to yourself, oh, they're talking about the inverse. Step 1, switch the x and the y. Step 2, solve for y. And you can do this on your own. Let's just do, so for example, example 1, y equals 2x plus 1. So this is the function. To find the inverse, we switch the x and the y, and we solve for y. This is the inverse function. And then maybe we had some other functions. You were introduced to y equals 2x plus 1 over x minus 3. The question was, how do I find the inverse of that? Well, you switch the x and the y. And the idea is, how do I solve for y? Well, the trick is you cross multiply. So you have xy minus 3x equals 2y plus 1. I'm going to bring all the y's to the left. I'm going to bring this 3x to the right. I'm going to factor out the y here. And then I'm going to solve for y. So the idea is you found this is your function. This is your inverse function. Now, a kind of interesting thing about the function and its inverse function that you might have learned last year is that if you graph a function and its inverse on the same axis, which you're really not supposed to do, but you'll notice something interesting. So what I'd like you to do now is I want you to graph. I would like you to go to Desmos. Right now. And I want you to graph y equals x squared in the first line. And then I want you to graph x equals y squared in the second graph. I want you to tell, what do you notice? Well, good. Well, if you also graph y equals x, you'll notice that the y equals x squared, and this is y equals x squared. And if I graph the function, this actually ends up being x equals y squared. And they are inverses because I switched the x and the y. You'll notice that they are actually reflections through the line y equals x. And I can draw in the line y equals x. Right? And you'll notice that it's a reflection of each other. It's kind of cool, right? Go back to Desmos and try another one. For example, y equals sine of x, and x equals sine of y. We're going to talk about how to solve for y, but I just want you to visually, and put the, y equals x in there, and you'll see, oh, that's kind of cool. You'll get something like this. And then you get, let's see, it looks like it's a, it looks something like this, like a, and you see like it's reflection. So this is x equals sine y, and you'll see y equals sine x, and you'll notice, oh, Mr. Adler, yeah, when I graph a function and the inverse, it's a reflection through the line y equals x. Nice and pretty, but there's an issue here. What's the issue with those? That you kind of think, if you actually graph these, if you pause the video and graph these two functions, it doesn't cause a problem. There's a clear problem in those graphs. And can anyone say what it is? Can you think about it for a second? Yes, these are not functions. X equals y squared is not a function, and the inverse of sine, whatever this thing is, it's not a function either. That is a problem because I want to be able to do all these things with my inverse also. So, first of all, how can I immediately recognize that the inverse of y equals x squared is going to give me a problem. How could I have immediately recognized that y equals sine x, its inverse was going to give me a problem, or not be a function? And you could use something called the vertical line test. So once again, so the inverse of y equals x squared, where x is all the reals, is not a function. And let's visually take a look at that. Let's see what the problem is. Well, for example, I see that -2 and +2 both go to 4. Right? Well, where's the inverse taking 4 back to? Well, it's taking it back to -2, and we know from our study of domain range and relations and functions, we can't have that. Now, this is known as a many-to-one function. So the inverse of a many-to-one function is like 1 to many. That's no good. So what do we have here? So if the function is not 1 to 1, that is, an x value goes to a unique y value. That is, each x value corresponds to a unique, let me get a new pen. Corresponds to a unique y value then the inverse is not a function. It's not a function. And there's a quick way to determine if your function has an inverse, and simply put, it's called the horizontal line test. The horizontal line test. Simply take your ruler and draw a horizontal line and say, oh, you know what? There's 2 x values that correspond to the same y value. That means that y value is going back to 2 x values? No good. What's going on with sine? Well, sine, you learned last year, sines repeat. I mean, look at all these x values, you have the same y value. That means there's just one y value in the inverse that is going back to all these x values. We can't have that. So if use the horizontal line test, and simply put, horizontal line test. Well, what are we going to do about that? If the function passes the horizontal line test, then its inverse is a function. Well, so this is something we're going to need to think about a little bit, not a big deal. The question is, what can we do? What can we do to the parabola? What can we do to the parabola so that when we reflect it over the line y equals x, its reflection is a function, and it turns out restrict the domain. So in Desmos, what you're going to do is open squiggly, literally with no comma, open squiggly bracket, 0 less than x less than 10, close squiggly bracket, and then for the next one, do open squiggly bracket, no comma, no space, 0 less than y is less than 10, open bracket, and you'll notice that, sorry, my computer went out. You'll notice that the new graph, you'll notice your new graph looks something like this. So here's my, once again, I'm not on decimals, but you can see, so the original parabola is now, looks like that. That's this function here. Once again, we started at 0, we restricted it, and the reflection through the line y equals x. So we draw the line y equals x. The reflection is now looks like this. Once again, it's restricted. Now, I think Joshua asked me a question about why is it not the same, and that's the idea, is that once we restrict to only positives or negatives, this is the point. This is the image we get. So we took off the left branch. That means for the inverse, we took off the bottom branch, and now our inverse is a function. So this is x equals y squared, and this is y equals x squared. Once again, with the domain and the range restricted. Okay. What's next? Restrict the domain. Couple of cute little things. Once again, this is just a lot of arithmetic, a lot of algebra. So you're going to have to practice this. Please just go through these problems. Let's start with a couple of things. If you do the composite function of two inverse functions, it makes sense. Well, it's x. It turns out that you could also mix up the composite functions. This is a rare case. Composite functions are not commutative. So composite functions are not commutative. That means f of g of x does not necessarily always equal g of f of x. And we saw that in the first example. If you go back in your notes, you'll see that f of g of x was 2 times the radical x plus 6 plus 5, but g of f of x was the square root of 2x plus 11. Now, there are some, that of course, in math, there's always exceptions, and this is one of them. It turns out that if you take a composite, so f of g of x equals x, then, side note, then f of x and g of x are inverses of each other. And that totally makes sense because the idea is g of x takes my x value to y, and if f takes me back to x, it's an inverse. It's clear. Sometimes that looks weird in the textbook, but the cool thing is that you can flip it around. If f of x goes to y, that g of x, g takes that y value back to x. So a trick question I ask my students sometimes, I'm like, what is f of inverse of 3? What does that equal? And the students say, well, I don't know, Mr. O, what's the function? And I go, I'm not telling you. Well, think about it. The answer is 3. Think about that. What else do you need to know? If it turns out, another cute little thing, if the function is equal to its inverse, then we say that f of x is a self-inverse function. Self-inverse function. So obviously, you see the algebra problem showing up here, like, find a value of k for which a function is equal to its inverse. It's a lot of arithmetic, a lot of algebra, but you'll figure it out. The last really neat thing, this is really awesome. So what they'll say is, they'll give you a function. They'll give you a function, right? Can you see over here? Yeah. They're going to give you a function. They'll be like, f of x equals, I don't know, the square root of, 2x plus 5. And they will say to you, what is the range of the inverse? In some, they'll say, what is the range of the inverse? And kids are like, oh no, I have to, first I have to find the inverse, and I have to do all these. It turns out you don't have to do the inverse. It turns out that the domain of the function is equal to the range of the inverse. So in this case, we say, okay, so for f, the domain is x is greater than or equal to, we know that for the domain, 2x plus 5 has to be greater than or equal to 0. So 2x has to be greater than or equal to negative 5. X equals greater than or equal to negative 2.5. Therefore, the range, this is kind of cool, I love this. The range of the inverse is y is greater than or equal to negative 2.5. And some of you are thinking, you learned from last year, it works also for the range and the domain. So the range of the function, finally, the range of the function is equal to the domain of the inverse. And you say, is that true? Yeah. If you look at that, and that's easy. So they say, what is the domain of the inverse? And you say, okay, well, I know the range is y is greater than or equal to 0, and therefore that's the domain of the inverse. So the domain of the inverse is x is greater than or equal to 0. Obviously, you can figure that out. Y equals square root of 2x plus 5. Y squared, x equals square root of 2y plus 5. X squared equals 2y plus 5. X squared plus 5 over 2 equals y. Yeah, yep. Minus. Yep. And you can look at these two graphs. And you can see it works out nicely. That's it. I'll put the homework up. Good luck.